All right, good day, everybody. Welcome back to KodeCamp DevOps Bootcamp. Um, we are glad to have you back. Last time we spoke about containers and we looked at how to create containers and work with containers in Docker environments. Today we are going to look at container orchestration, which is how we manage multiple containers in an environment where we have numerous applications running on different containers. We need a way to manage and orchestrate these many containers with easy, stable, and effective, reliable processes. So that's what we are going to look at today, how to manage containers, how to manage multiple containers, which is all covered under the term container orchestration. So let's quickly get into that. What is container orchestration? So container orchestration is the automated management of containerized applications across multiple containers. Um, we can have applications running on different containers, either as a way to um, either having the same application running on many containers in order to make it more handle more processes, handle more workloads. Um, in the event of scaling out a single application, we can have that application run on multiple containers, or we can have many applications making up one product running on many different containers, and we need a means by which we can effectively manage these many containers, right? So we use container orchestration processes, we use container orchestration tools to manage multiple containers within an environment. It helps us to ensure the efficient deployment of applications to the containers. It helps us to automate the scaling in and scaling out of the processes as the case may be. If we are working at with a level of workload or a level of traffic that needs more containers to be able to handle the workloads that we are handling, that we are working on, that we are um, meant to be processing, we will need to be able to scale out and scale in as the 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 case requires. We also need a means to monitor the performance, right, of the applications within containers. And to do that in an automated fashion, we need container orchestration tools as well. Also, with issues of maintenance of the containerized applications, container orchestration tools also help us to do this. So container orchestration helps us to effectively deploy, scale, monitor, and maintain containerized applications across multiple containers and multiple container environments. There's a depiction of a container orchestration tool here that is orchestrating different containers running within different nodes. Now, a node is simply a machine where you can run applications. It could be a computer server. It's mostly a computer server. It could be a unit of a machine that you can use to run your containers on, right? Okay, so container orchestration tools. Container orchestration? How did this come about, right? After the introduction of containers within the application scene, um, containers became more and more popular, more and more prevalent, more and more used and relied on within um, software engineering teams. We began to see that containers were more widely used for deployments and running applications. And even the architecture and the way we design applications changed with the introduction of containers. In the sense that, for example, in the past, you can see what is known as a monolithic architecture of an application, where an application is built with all of the parts, all of the components within a single product code, right? Within a single application code. You can have the front end built within the same code, the back end, processes and the various logical operations built within the same monolithic code and deployed together. The problem with this comes in the form of two major things: fault tolerance and um, independent scaling. So if one part of the application begins to have a problem, we see that the entire application can be affected by that. Also, um, different parts of applications might need scaling without other parts of the applications needing to be scaled. For instance, you can have a single instance of your front end being able to manage as much traffic as you need, but the back end processes, for instance, might need to be scaled out, which means just adding more instances of the code in order to be able to handle the traffic. But to do that in a monolithic architecture, you have to scale the entire application to scale just a single part. So the introduction of microservice architectures, which was greatly supported by containerization and containers, became a thing and became more widely accepted and more widely used. So this also popularized the concept and the use of containers. How many microservice architectures work would have an application broken down into various services that handle different kinds of operations. So you can have one service that handles user requests, another service that handles talking to the database, another service that handles the processing of information, another service that could handle the front end. So all these services loosely coupled together into the same one application. Now, with this, you see that you can a failure in one part, one service might not necessarily affect the entire application, and you can now scale out independently. So I just explained monolithic and microservice architectures for building applications, right? So with that, microservice architectures, as they were more widely accepted, popularized the use of containers, but they also put forth the problem of managing multiple containers, because a microservice architecture would work with many different containers that run the different services. So with microservice architectures, you now have multiple containers on which your application runs. You now need a means to manage and orchestrate these multiple containers. And this is what brought about the development of the concepts and the tools used for container orchestration, right? Um, so as containers became more popularly used in deployments and microservice architectures started being widely used in applications. Its challenges now became prevalent in that's brought about containerizations. And some of the challenges that arise with manually trying to orchestrate your containers include scaling problems, deployment configurations, complications. Scaling becomes a problem if you want to scale, if you want to manually handle containers, which is very difficult these days. Deployments, how are you going to deploy to these various containers? It becomes more complicated. Being able to troubleshoot issues, being able to find problems. You have many containers. How do you find problems? How do you find when there's a problem in one container as opposed to another one? That becomes a challenge, troubleshooting. And also how to have these containers send messages, send packets between each other, how to have them communicate, how to have them discover each other and send communications to them becomes another problem, another challenge. Now, various components, various parts of container orchestration came in to solve this problem. The first we can look at is provisioning. That is the allocation of resources to containers. Different containers running different kinds of workloads, running different kinds of applications would need different kinds of would need different kinds of requirements, right? The same container running a database application might be different from the memory resource allocations you give to a container running, say, an Angular application for the front end user facing interface, right? So different kinds of resources would be requested from different kinds of applications within containers. Container orchestrators help us to handle the provisioning, that is the allocation of resources to different containers. Another one is the deployments, being able to roll out changes, roll out application updates, application changes to containers and to deploy new containers. Container orchestrators also help us to be able to automate this process as well. It also helps us to automate the process of scaling, that is adjusting the number of containers based on the demand, either scaling out, which is increasing the number of containers, or scaling in, reducing the number of containers that are processing a particular workload or responding to a particular request. Keeping track of the container performance and the health. Are the containers working? Are the containers up? Are they doing what they are meant to do? Are they responding to traffic? Are there errors on my containers? Container orchestration helps us to monitor and observe our applications in real time. It helps us to work on upgrading, applying updates to containers without downtime. We can roll out updates seamlessly without having to stop and recreate the application. So container orchestrations help us to handle that. Also, handling traffic between multiple containers. Container orchestration tools can help us to handle the allocation of traffic through load balancing techniques, help us to handle the balancing of traffic and the routing of traffic to different containers in order to have a balanced handling of workload, handling of traffic. Also, the security of containers. Container orchestrators help us to secure our containers. Security becomes a great concern when working with containers, right? So we need container orchestrators and container orchestration processes to help us improve the security and security postures of our various containers. Containers orchestrators also help us to do service discovery, which is basically being able to know that a particular container, a particular service exists, and being able to find it so that you can send traffic to it and receive traffic from it as well. Then finally, health monitoring, which we've also spoken about previously. Taking a look at a simple container orchestrator, you can see right here is a cluster of containers. We have a physical infrastructure, we have VMs, and then we have an orchestration tool, an orchestration engine that runs various applications in different namespaces. We can also see a cluster environment for a container. And here we have a node which is public where we can deploy certain containers that we want to be public. We can also have a different node that can run other containerized applications to us if we want that to be in a backend interface. We have another node for cluster management. We have the nodes connected to different services within our, our environment. Benefits of container orchestration. Now, container orchestration helps us to automate the process of scaling within our containers. Helps us to automatically adjust resources based on request needs. It helps us to automate the process of deployments. It helps us to automate the process of scheduling, which is knowing the right node, right, to allocate a container to allocate a set of containers to. Scheduling helps us to know that if we have 5 nodes and we are running an application that we want to have at least one instance of this application on each node. Say maybe you want to run a monitoring application, right? And you want a single instance of this your application to be deployed to each of your nodes. Doing that manually means could produce some issues, right? You might mistakenly assign 2 instances of your application to one node. And if a new node is created, you have to manually install that application on that node. But with container orchestration, you can automate the process of scheduling that application across your various nodes, right? Service discovery enables containers to find and communicate with each other seamlessly. It's almost unimaginable handling there are some applications, there's some software teams that handle up to hundreds or thousands of containers. Being able to keep track of all of that manually is a lot of operation overhead, right? So container orchestration helps take that off your hands and do service discovery for you so that containers are aware of each other and can communicate with each other. Benefits, container orchestration also has benefits of helping us to enforce security policies, enforce networking policies, manage our secrets for us, and ensure secure communication, encryption of traffic within our cluster, and also monitoring as well. So some popular container orchestration platforms. Container orchestration platforms in the industry today are separated into 2. We have the managed platforms and the self-managed platforms. So the managed platforms, usually with cloud providers or cloud services, cloud providers could usually, as an offering, as a service offering, provide a managed Kubernetes service to you, where they manage most of the control plane components, which I'll come to and explain later. They manage most of the control plane components while the worker plane components and the worker plane operations are handled by you. So if you're working with a smaller team, that takes a lot of operations workload away from your hands, right? Because you have a team with the cloud provider or the managed provider that's managing a large part of your orchestration for you as it relates to the control nodes and the control components. We have this in AWS in the form of EKS, where we have Elastic Kubernetes service from Amazon. We have Google's Kubernetes engine, GKE from GCP, Google Cloud Platform Provider, and AKS, Azure Kubernetes service. It has the advantage of reduced operational overhead and easier management. There is also the self-managed container orchestrators, which include Docker Swarm, Apache Mesos, HashiCorp Nomad, Red Hat OpenShift, and SUSE Rancher. We can also have Kubernetes deployed within your environment using tools like kubeadm or K3s, where you can deploy or set up a Kubernetes cluster and manage your resources by yourself in a self-managed fashion. Okay. So these are some of the container orchestration tools that are in the market today. Kubernetes has, however, become the de facto container orchestration tool. It is widely used, more widely used than other orchestration tools like Swarm, Mesos, Nomad, and OpenShift. OpenShift even works with is a Kubernetes distribution, even. So Kubernetes is the most widely used container orchestration tool in the industry today, and that's what we are going to be the tool we are going to be working with for container orchestration within our bootcamp. So let's take a look at Kubernetes. Okay, so Kubernetes is an open source orchestration tool which was originally developed in Google. It was used internally within the management of their container clusters. It was back then known as a tool called Bug. But Google donated or made this platform open source around 2015, 2014. So they made it open source around 2014, and it was now adopted by the Cloud Native Computing Foundation in 2015. The Cloud Native Computing Foundation is going to be your best friend the more you work with container to the more you work with Kubernetes. They have a lot of tools that perform a lot of processes for you and are open source, which means that you don't have to pay for them. You just have to work with them. They have a lot of contributors that are working to improve and keep them stable. So Kubernetes became popularly used from 2015, 2014, 2015, and has become the de facto container orchestration tool for most engineering teams today. I personally work with Kubernetes and I'm in love with it. Control the Kubernetes architecture, how Kubernetes works, how it's designed is this. It is divided into two major parts: the control plane, which has the job of managing the worker planes, the worker nodes. So the control plane has components that manage the worker nodes, right? So Kubernetes works basically with a master-slave architecture. You have your control plane and you have your worker plane. The control plane handles and sends commands and does the orchestration of the master plane. The control plane has components that you can use to basically control the master plane. Most of your workloads, most of the applications that you'll be deploying will be deployed to your worker plane, while your control plane will have the controllers that control the things that you have on your worker plane. Let's take a look at this in a more visual manner. So here you have your control plane, which has components such as etcd, which is basically the brain of your Kubernetes cluster. It contains all the metadata, all the information about your Kubernetes data, which is kept in a key value store database. You have the controller manager, which manages all of your other controllers. You have your scheduler, which is in charge of deciding, making the decision of what container, what pod goes to what node, right? We'll talk about pods and nodes later. We also have the Kube API server, which does the communication, which sends commands to the kubelet on which is on every node. So with the connection between Kube API within the control plane and all the kubelet services running on each node, you can send commands to the kubelets which perform executions on your nodes. You can receive information about what is going on your node from the control plane as well. So this is the basic architecture of a Kubernetes cluster. It's a master slave leader follower architecture, which is seen across many applications that we know today. The master slave and leader follower architecture. So let's take a look at some of the components on the control plane. First, we have the Kube API server. The Kube API server is the component of the Kubernetes control plane that exposes Kubernetes objects by serving REST operations and providing a front end to interact with the cluster, right? So most of the objects, Kubernetes in itself at the basic level is an API set. API works with APIs, API calls, and REST APIs, right? So you send a request to an object and you get a response, right? So the Kube API is what you use to interact with the rest of the cluster. It has the job of interacting with the other API objects that form Kubernetes, right? So that's your Kube API server. It's basically the brain of Kubernetes. It does the communication, the sending of information, the receiving of information, the execution of commands and instructions, right? Then you have your etcd also on your control plane. Etcd is a key value store. That is, it has a key and a value, name and the name. That's a key value store. So it's a key value store that serves as the database or the data store for all of your cluster data. In a production environment, your Kube ACI server should be made as reliable and as available as possible, because losing your using your etcd components is like losing all the data in your cluster, right? So it's designed to be highly available and should be configured to be reliable with backups, especially in a production cluster. You also have your Kube scheduler as one of your control plane components. Your Kube scheduler is a component that decides which node to assign pods to. When you have new nodes created, they need to be deployed on a particular node, right? A pod is used to hold containers. It's used to hold related containers, right? So you can have a pod that contains one container. You can have a pod that holds more than one container. So a pod holds a container and helps to have that container deployed within the node, right? So a pod holds containers, right? Okay. So when new pods are created, that is when new collections of containers within a pod are created, they need to be scheduled, they need to be deployed, they need to be put on a node where they can run, right? So the Kube scheduler has a mechanism for making decisions on the most appropriate node for a pod by considering various factors, which include the resource requirements of the node and the resources available on the resource requirements of the pod and the resources available on the node. You also have hardware and software policy constraints. You have affinity and anti-affinity specifications. So I can decide to have a certain type of application within a pod deployed to a certain type of node. Affinity, anti-affinity. Affinity is basically the concept of having a pod attracted to a certain kind of node. So if I have a certain kind of application, running on a container, that is maybe a machine learning, that runs a machine learning model. And I want this particular kind of container to be deployed to a node, a server that has a strong GPU processor, right? To be able to handle that kind of node. I can create some affinity roles and write some affinity specifications that say this kind of application, this pod should go to this kind of node. I can also say this kind of application should never be deployed on this kind of node, right? Maybe I say, okay, once this application is deployed to this server with a GPU, no other application of this type should be deployed to that server. So once the cube, I can write an anti-affinity specification that to tell this kube scheduler, when you see this application already deployed on this server, don't put another one of this kind on that server. So that's basically the concept of affinity and anti-affinity, right? So also data locality, internode workload interference and deadlines. So the kube scheduler uses these factors and more to decide on what node to put a particular pod, right? You also have the kube control manager, which this component is basically responsible for managing and running controller processes on your cluster. Some controller processes include your node controller, which controls your nodes. You have job controllers, you have ingress controllers, you have service account controllers, you have endpoint controllers. We'll talk about this more when we go into practically working with Kubernetes and Kubernetes objects. Okay. Take a look at what our worker plane looks like. So in the worker plane, you have your kubelets running on every worker plane. Your worker plane is basically where you have your nodes, right? So you can have your control plane and your worker plane. You have control nodes, right? And worker nodes. Control nodes, you can have more than one control nodes, depending on how reliable, how available, how critical your cluster needs to be. So your control plane is basically just speaking to your worker node. Your worker plane is basically speaking to your worker nodes, right? So each worker node, each server, each node should have a kubelet. Now, this kubelet is the Kubernetes agent that runs within your node, right? It's responsible for managing the pods and managing the nodes for Kubernetes. It's responsible for receiving instructions from the kube API server. So your kube API server speaks to the kubelets node running on every worker node. That's how your kube that's how your control node uses the kube API to talk to your worker node through the kubelets, right? You also have kube proxy, which does the which is your network proxy that runs on each node. It's responsible for implementing network rules, network policies, and allows network communication between pods within the cluster and to destinations outside the cluster as well. So setting up and controlling the networking of your container environments is the job of your kube proxy. Container runtime. Now, your container runtime is really important within Kubernetes. It is your runtime that's responsible for managing containers in your worker node. So you need a container engine, which is also known as a container runtime, running on your worker nodes as well. So Your worker node consists of your kubelets running on your worker node, your kube proxy running on your worker node, and your container runtime as well running on your worker node. Your control plane consists of your kube API server, your etcd server, your kube scheduler, and your kube controller, right? So that's your control plane and your worker plane, your control node and your worker nodes in the master slave architecture of Kubernetes. All right. So that is our foundational class on container orchestration and Kubernetes. This class is a highly practical, highly hands-on class, and we'll go into our hands-on classes exclusively from our next class. Thank you so much for being here and for engaging, for listening to this class. We can take some questions now based on what we have learned so far and discuss more on what we've learned. So are there any questions? Okay. Okay, we have a question from Johnny Doe. Please go ahead.
Yeah, good evening, sir.
Hello, good evening.
Yeah, thank you very much for the class. There's something I just want to confirm. While I was reading about the architecture of Kubernetes, like over the weekend, so I found out that in the control plane, there is another component that I read that you didn't mention. It says Cloud Controller Manager. So I don't know if it's the same as the controller manager or if it's different.
No. So we have the controller managers that handles different controllers within your Kubernetes control plane cluster. When you have your cluster deployed within a cloud environment, especially when it is a managed cluster, right? Say you have something like the managed clusters we talked about. Let's go back there. We have AKS, GKE, AKS. Each of these kinds of clusters managed and run on a cloud provider has a specific type of control manager called the cloud controller manager, right? That's helps it to interact with the that cloud environment that it's running in, right? However, Kubernetes itself can be run within an environment, right? So it's not a component that you will always see. You see it mostly when that cluster is within a cloud environment. It's a managed cluster or running within a cloud environment. Say if I deploy if I get a set of nodes, right, maybe a set of servers running in my home lab, right, and I deploy Kubernetes on it, I will not need necessarily a cloud controller manager. I hope you get that.
Okay, yeah, that was very clear.
Yeah. So thank you for that question. Very important.
Thank you, sir. I still have another question.
Please go ahead.
Okay, so I know you said we're going to start practicals next week, but I just want to ask if which one will you recommend for us to be practicing? Is it Cube, ADM, Minikube, or Kind?
I'll recommend, for the sake of this class, Minikube, because that's what we are going to be working with for this class. However, you can also try your hands out with Cube ADM. But for the sake of this class, we are going to be, the tool we are working with in this class is Minikube, right?
Okay.
So when we're talking about our cloud, when we're learning about cloud platforms, I mentioned that the cloud provider that we are working with in this class is AWS. However, there are various other ones that you can also get your hands dirty with, right? So for this class, we are working with Minikube.
Okay, thank you. I think I'll make sure I download it before next class then.
All right. Thank you.
Thank you.
Hello. Are there any other questions? Okay, we have a question from Nick Oyema. Nick, please go ahead.
Okay, thank you, sir. I'm a bit lost. I don't know what's Minikube, so that we can also download ahead. Then secondly, these components you mentioned now, is this something we need to memorize? Or this is something we need to memorize and we will see during the practical, or we will just see practicals and do practicals, like the hands-on? Do we need to start memorizing? Is it of any benefit to start memorizing these components?
Okay, so so we've talked about Minikube before in class, and we've done our setup for Minikube. So yeah, so try to review our classes. It's also important to follow up with the class and revise everything that we are learning. Everything we talk about within our class is going to be important for the practicals. So we should know all of these things. Yes. All right. Okay. Thank you. Okay. Okay. So I guess there are no more questions now. I'm sure a lot of questions will arise when we start working on these things practically, and more understanding will come to it. So for now, thank you so much, everybody, for joining the class. I really hope you enjoyed it. I really hope you understood it, and I really hope you're interested in learning more about this. Thank you once again for joining, and do have a great day. Goodbye.